Good morning, folks. This is lecture 12 on February uh, 14. And I want to remind you that we have a test coming up. Test number 2 is coming up on Thursday, the 16th, and this material will be on it. Okay? So, the agenda for today is talk about some measurement devices, and among those, we're going to refer to accelerometer and seismometer regions of the measuring device that I'm going to show you. Okay, so let me remind you that we did this problem called base excitation, and as an application of that, I told you that you may think about the suspension of a car going over a bumpy road. So the suspension on it, the profile of the road is being applied. We also did uh, another scenario. We talked about another scenario that maybe there is a machine compressor or a fan or a press machine that is being used in a certain area, and because of the vibration of that machine, maybe the fan or the compressor, the ground vibrates, moves, and this is going to be this movement of the ground may be transferred to another perhaps platform where on it sits a machinery, delicate machinery. So the base of that platform where the machine is, this delicate machinery is sitting or instrument is sitting, is subject to the movement which is being transferred from that other machine to the through the ground to this delicate equipment. But what we want to show you today is that another application of this concept of base excitation is the design of an accelerometer. So, first of all, any device that changes mechanical motion into a voltage is called a transducer. For example, when you take an accelerometer, the motion of the ground, the motion of the thing that it's being attached to will be picked up by this thing and is going to be converted somehow into a voltage, and therefore it's a transducer. Here is a let me see. This is an old-fashioned mechanical accelerometer. So notice that you have a casing, and the base of this accelerometer, this casing is attached to something that is moving. So the thing that we're trying to find an acceleration of is this cross-hatched region, which on it, this accelerometer is mounted. Now, inside of that uh, uh, casing, there is a mass, inertial mass. You can see that, a mass, and there is some kind of a spring and a damper. So as the base moves, vibrates, this mass also will be vibrating up and down. And based on the relative motion of the mass with respect to that base, a voltage is being produced. Now, the first thing that we need to do is to find the equation of motion of this mass, and it's very simple. If you draw the free body diagram of this mass, there are two forces that are opposing its, for example, upward motion. One is the spring force, which is the k times the relative distance, relative stretching or compression of the spring, times the damping coefficient, the difference of the velocities. Now remember, these are relative motion and relative velocity of the mass with respect to the base. And of course, the Newton's second law said that sum of all the forces, whatever they are, wherever they're coming from, is equal to mass times acceleration, and that acceleration is the inertial global coordinate system, which that's why we use x double dot. X is measured with respect to the equilibrium position, which is a fixed location in the space, so it's an inertial value, inertial coordinate system. Now, here's the expression of what I told you. And what we do know is that this y, we know what it is. Y is the motion of the base. So y, let's assume that it's a sinusoidal harmonic. Okay, let's assume that it has an amplitude and a frequency, which is called omega b, or base frequency. Now, if I define as variables at the difference between x and y. So it's not y itself, it's not x itself that we're talking about, it's the difference of these two. Then that equation can actually be written in terms of z. For example, this x minus y is going to be simply z. X dot minus y dot is simply going to be z dot. So if I wrote it and cleaned it up, okay, cleaned it up, you're going to get this equation. Now, here, keep in mind that here, I, I, I'm going to have x double dot, and x double dot is you can get it from this expression. X double dot is simply z double dot plus y double dot. So we get rid of that x double dot by replacing it with z double dot plus y double dot. And remember, y double dot, the second derivative of this thing, is just the derivative of cosine twice. That's why you're going to get cosine back. And there's going to be omega b coming out twice, so it's going to have omega b squared. Okay, and that m is coming from the fact that we replace this x double dot with z double dot plus y double dot. So this equation, actually, we have seen somewhere. This equation, we have seen it when we did uh, the stuff 2 weeks ago, except that the 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 variable that was sitting on the left side was not relative displacement, it was the global displacement. We have seen something like mx double dot plus cx dot plus kx equal to something like this on the right hand side. Okay, now uh, the only difference here is that the same equation applies for the relative motion of the mass with respect to the moving base uh, uh, in this form. Okay, so we know how to solve this because we have solved it when this was x. Okay, now the other thing is that this accelerometer that I showed you, generally speaking, uh, this is a generic accelerometer. They used to be all like this. You don't find things like this anymore. So it's a generic but a classical one, but it's a good enough to explain the concepts behind the accelerometer equation, which allows us to actually get information about how to measure things. Okay. Just remember that this is the relative mass displacement. Okay, so I wrote this thing here for your perusal. So it's the same equation. And as I said, we have seen something like this in earlier lecture. The only difference is that these were x instead of z. Now, the solution to this, we found this. If you go to your notes, you see that we found x equal to, but here's z equal to. So this is the amplitude of the relative displacement. This is the amplitude of the relative displacement. This is the phase of the relative displacement. So what we had before was a big X here, something like that, a big X, cosine of omega bt minus theta. Okay, so if you see what you've got here, uh, this is what it's going to be looking like. Now, uh, I'm going to redo this thing because generally speaking, we don't want omega n and omega b to be hanging around. Now remember, this omega n is the natural frequency of that device, okay? In other words, square root of k over m, okay? So, but we don't want to leave it like this. We want to write things in terms of frequency ratio, namely omega b over omega n. And if you do that, if you clean this up and find the big Z, which is actually this thing, divided by big Y, which is the motion amplitude of the motion of the ground, you come up with this expression. So if you give me R and you give me zeta, then I can, and you give me the amplitude of the base, which actually we are trying to measure. Remember, we're trying to measure the acceleration. We don't know what big Y is. We're trying to measure it somehow. Then I can give you big Z. Okay. Now, here's the phase difference. Okay. So amplitude of the relative displacement is that big Z. Amplitude of the base displacement is big Y. And this is written again, once again here, and I'm going to plot this. Plot this. Notice that this Z over Y, this is Z over Y, relative displacement ratio, is a function of the frequency ratio, function of R. And if you plotted that, you're going to see that it actually starts at 0, peaks, and then it drops down and it goes all the way to 1. Now notice that when you look at values of frequency ratio which are very large, in other words, R being very large, frequency ratio omega b over omega n very large, and another way to interpret that is saying that omega b is much, much larger than omega n, or omega n, the natural frequency of the device, is much, much smaller than omega b. So anyway, R is large, so it's here. This is, notice that it doesn't matter what the damping coefficient is, damping ratio is, because remember, this thing depends on the value of xi. It doesn't matter what the damping ratio is, they all approach kind of 1. This ratio almost approaches 1. And what that means is that the relative displacement of that mass is actually the amplitude of the vibration of the base. Z over Y approaching Y means that Z is almost Y. So remember, we are trying to find the Y, the base motion. So we are trying to kind of estimate the big Y. Of course, accelerometer will need the derivative of little y, but this is just the Y itself. This region where R is very large, in other words, omega b over omega n, very large, is called the seismometer region. And another way to look at this, as I said, you can have omega n very small. If omega n is very small, the ratio omega b over omega n will be very large. So the seismometer region, okay? And omega n being very small, that means the mass of that thing it can be very large. Seismometers usually have a big mass. On the other hand, if you look at this region on the left side, the accelerometer region, notice that regardless of what these these damping ratios are, this ratio will actually approaches 0, okay? And this is called the accelerometer region, and we're going to come to that in a minute. And by the way, one more time, here you want R to be very small. That means you want omega n to be large, or very large, or large compared to omega b. If R is to be small, omega n must be very large. And if omega n is very large, the formula for omega n is root of k over m, and means that m is very small. In other words, this is why accelerometers have a small mass, can be fabricated to have a very small mass, because then they give a large omega n, which is the region that you want to be at. Now, let's go back to one more time to the seismometer region over here. If R is bigger than 3, you can see that. Z and Y are almost the same in the seismometer region. And this means that the relative displacement of the base and relative displacement of the mass, or displacement of the mass, they're almost the same. So accelerometers can be used to measure harmonic base displacement if the frequency of the base displacement is at least 3 times, see, R bigger than 3, is at least 3 times larger than the accelerometer's natural frequency. In other words, if you look at this expression, all it says is that R is bigger or equal to 3. Now, here's the story. If you are in that range, in the seismometer range, and we'll get to the accelerometer range later on, if you're in the seismometer range, the measured displacement, because what you can measure is that Z causes the voltage in the device to be extracted. That Z causes a voltage, and basically, if you know the voltage, you know the displacement. Over the true displacement is that expression. This was big Z over big Y, okay? So R squared over this, okay? Now, let's look at the case. Let's go back to the accelerometer region. Let's look at the case where R is small, okay? Again, we wrote down the expression. I wrote down the expression for Z over Y for you. And notice that this R squared simply means omega B squared over omega N squared, right? This R is nothing but omega B over omega N. And when you square it, omega B squared over omega N squared. And if you rearrange that, you bring the omega N squared multiplied by this, omega B squared, you leave it there, okay? And if you take that, multiply both sides by Y, big Y, you get this expression. And let me remind you that this is the acceleration of that mass inside the accelerometer. Remember omega n squared? And this is the acceleration of the base, the amplitude of the acceleration of the base. So this thing is proportional to the maximum acceleration of the base, because acceleration of the base is going to be omega b squared big Y times, remember, it's time, of course, it's times this, but it's going to be times uh, second derivative of cosine, which is going to be another cosine, okay? So, and this thing, you can measure Z. The voltage will tell you what Z is, and you have to know omega n, the natural frequency of your device. If you know that, you know the product on the left, and basically you know the maximum acceleration of the base, which is right here. Okay. Now, for small values of r, this quantity is proportional to the maximum base acceleration, namely that expression. And the proportionality factor, by the way, is just this thing that you see here. That magnificent um, uh, uh, dynamic amplification factor. Okay, big M. Remember this big M that we talked about 3 weeks ago, 2 weeks ago. So that's the proportionality factor. So uh, obviously you can read Z from the voltage, but you also need to know the natural frequency of your device to be able to find the acceleration using data processing, basically, to find the acceleration of the base. Remember, our objective is to find the acceleration of the base with this transducer, which is an accelerometer. Now, the effect of the damping on this coefficient. Remember, this coefficient is simply that 1 over square root of blah blah blah. Okay, 1 over square root of 1 minus r squared plus 2 zeta r squared. That is the coefficient of y double prime, because multiplied by omega b squared times big Y, right? The effect of the damping is shown here, and you can see that this is almost flat for zeta equal to 0.7. zeta equal to 0.7, it's almost flat to the left of 0.5, okay? So this expression, very close to 1, you can see that that proportionality factor is almost 1 when r is less than 0.5. Okay, now, the effect of the accelerometer, internal damping zeta, in the constant of proportionality, which means this is the constant of proportionality, uh, uh, between between the relative displacement and the base acceleration is illustrated in this figure, as I told you. And notice that constant proportionality is exactly this, and it shows that zeta equal to 0.7, almost we get the 1, the value of 1, as long as the frequency ratio is less than 0.2. Less than 0.2, almost 1. Now, this defines the useful range of the operation of the accelerometer. And what do I mean by that? We want this thing to be less than 0.2. Of course, it's always positive, and that will give you basically omega b between 0.2 omega n and 0. Or if you write it in hertz, fm is going to be the desired frequency to be measured in hertz. In other words, this thing uh, uh, divided by 2 pi, okay, divided by 2 pi is going to give you FM. And if you take this divided by 2 pi, you're going to get natural frequency of the accelerometer in hertz, okay? So generally speaking, uh, let's think about it like that. The mechanical accelerometers of the type that I showed you, this generic classic one, which to some extent is also defunct, but is very good for explanation purposes, is around 100 hertz. Now, what that means is the thing to be measured is less than 20 hertz and bigger than 0. This is a very low. This is a very low frequency range. Generally speaking, in many situations, the thing that you want to measure, it's the frequency of the motion of that gadget is, or the ground, for example, is bigger than 20 hertz. But this thing, uh, classical accelerometer, this is why these are no longer in use the way you're seeing it, is uh, you can do okay with it measuring acceleration of the things that uh, if you're talking about bass vibration, the frequency is less than 20 hertz. Now, if you use a piezoelectric accelerometer, that means that, well, I'll show you what that means. A piezoelectric one, it has a much higher natural frequency. In other words, from 100 hertz for this, you suddenly go to 80,000 hertz. And that means that the range of frequencies of the base motion that you can actually find the acceleration of can be up to 16,000 hertz. Here's what I mean. If you're using a piezoelectric accelerometer, and if the base vibrates harmonically, and the frequency of the vibration of the base up to 16,000 hertz, you can actually pick up that signal and use the accelerometer to predict the acceleration correctly. Now, when it comes to the accelerometer range, measured acceleration divided by the true acceleration is this ratio. And let me remind you what this thing was. This was omega n squared times big Z, and this one was omega b squared times big Y. And we showed that it is actually this. You just go back four slides, you see that measured acceleration over true acceleration, omega n squared big Z over omega b squared big Y was equal to this. In the seismometer region, remember, it will measure displacement, measured the displacement of the mass inside the accelerometer or seismometer divided by the true displacement of the base was this. But here we're talking about accelerometer range, so this is what we get. Now, what is this business of piezoelectric accelerometer? Now, notice that we had a mass, okay? And this mass is sitting on a material which is a ceramic or a crystal, okay? Not a ceramic crystal. And when this thing gets squeezed, when this material gets squeezed, it generates a voltage. You do not need a a, 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 a voltage supply or a battery, a power supply, in order to get a voltage here. Just the squeezing of this crystal will create a voltage. And by the way, it's the same true if you apply voltage to a piezoelectric crystal, its shape changes. So not only squeezing it will give you a voltage, if you give it a voltage, the shape of the crystal will change. That's why it's called a smart material, etc. Now, this has a very wide frequency and dynamic range. I already told you 16,000, uh, actually, yeah, for the gadget itself, it was 80,000 hertz, and when you multiply it by zero point 0.2, you got the 16,000 range that it's talking about, and it's a very good linearity range, so things don't go crazy because the function is non-linear, etc. And it's very robust. There is no wear and tear, okay, because it's just there's no this actually acts as a damper itself too, okay. So it's self-generating, so it does not need a power supply. There are no moving parts. Therefore, and finally, acceleration proportional output can be integrated to get velocity and displacement. So this is very robust. It'll give you acceleration over a wide range of frequencies that are you can measure. And if you take that thing and you integrate it, and uh, you get the velocity, and integrate it again, you get the displacement. Now, I already mentioned to you that if you take a piezoelectric material and somehow deform its shape, whether by stretching or torquing it or shearing it, etc., compressing it, it will generate a voltage. And of course, um, uh, pretty much when this casing accelerates, for example, or vibrates up and down, this mass will squeeze this crystal, and then stretches it, etc., and that's why, or relieves it from being squeezed. That's why it generate a a voltage, okay, and yeah. So for frequencies lying well under the resonant frequency of the complete mass spring system, the acceleration of the mass will be the same as the acceleration of the base. Okay, that's obvious. And the output signal magnitude will be proportional to the acceleration to which the pickup is subjected to. This is already something that we have discussed mathematically. So measured acceleration, or the true acceleration, was equal to, that uh, expression 1 over square root of dot, dot, dot. Okay, let's do some examples here. First of all, if you can use some, let's say we have an accelerometer and we want to find its internal characteristics, dynamic characteristic, and what that means, we want to find its omega n and zeta, or we want to find its k and, for example, damping value if you want. So uh, what you need to do is use another device to find the acceleration, and then use the one that you have and you want to find its characteristics in order to come up with the transducer's mechanical properties. So let's look at an example where an accelerometer is used to measure the oscillation of an airplane wing caused by airplane's engine running at 6,000 RPM. Okay, so we have an accelerometer. We want to use it to find the characteristics of that accelerometer 6,000 RPM when the engine is running. Now, uh, we know at this for this engine at this engine speed, we know that the wing from another device accelerometer experiences 9.81 meter per second squared. So you used another device and came up with 9.81 meter per second squared. It's not the one that accelerometer that you're interested in, but you use something else at the speed. It predicted that the acceleration is 9.81 1g. Okay, with the one that you actually want to look at, it predicted the acceleration of 10 meter per second squared. And it's the characteristics of this accelerometer that you actually want to determine. Okay, this is the other measurement device that predicted 9.81. The current measurement accelerometer that you want to find its characteristic showed a 10. Now we know that the accelerometer, some facts from that particular accelerometer that we are interested in, we know that it has a mass of 100 gram, okay? And we know that that particular accelerometer that we want to find its characteristics has a damped natural frequency of 100 hertz. Now remember how you get damped natural frequencies. You get stuff like that. You can do a free vibration and logarithmic decrement. Somehow it is done, and it's found out that the damped natural frequency of the thing that we're interested in is 100 hertz. Use the difference between 9.81 and the 10 to calculate the damping and stiffness parameters associated with this thing that we are investigating. So get the CNK for the gadget that's in your hand, and it predicted 10 meter per second squared. Okay, first of all, we know that measured acceleration over true acceleration, this is the measured acceleration, this is the true acceleration, okay, is equal to 1 over this. Okay, now remember, we need omega n. We need the natural frequency of the accelerometer that we're interested in order to be able to find acceleration. Okay, so we'll see. So just keep that in mind. Okay, now it's written here. So we know that the measured acceleration, this device that we are interested in, predicted 10 inch per second squared, and the independent one, the one that somebody else used, predicted 9.81. So uh, if we pretend that this is the true acceleration, then this ratio, which is 1.02, is equal to the right-hand side. Okay. Now we have one equation here, but there's two unknowns here. There's an r and there's a zeta, right? If you clean this up, you get 0.96. But we need one more equation between xi and r in order to be able to solve this thing. Now, and here's what you're going to do. We know that for the accelerometer that we're interested in, we're trying to find its characteristic, the damping ratio, the damped natural frequency is related to the natural frequency through this, right? This is stuff from test one. So if you look at the ratio omega b, if you look at omega b over omega d, just a matter of putting omega d here, and omega b over omega n is what we call r, divided by that. The moral story is that we are told what the wing vibration frequency is, 628 hertz. I think that was rad per second, if I'm not mistaken. Yeah. And omega d, we told that that accelerometer that we're interested in has a damped natural frequency of 628. So here is my second equation. One equation was this on the top. Another equation is here. You have two equations and two unknowns. If you solve these two together, you get two values for zeta. But this one is we throw this away because we're interested in the underdamped case. We throw this away, and of course you get the value of r. If you have zeta and if you have r, you can find the c and the k. So let's see now. First of all, if you have zeta, because omega d was given to you, you can find natural frequency 758. Remember, you need this in order to predict acceleration, because the acceleration of that thing, accelerometer, is the true acceleration of it is omega n squared. You need this times the big Z. Big Z is what's coming out of the as a voltage output. Okay. Now, and if you want the value of C, you know how it works, 2m omega n zeta. The mass of that, the mass inside the accelerometer, you were told is 100 gram or 0.01 kilogram. And omega n we just calculated, and zeta is just estimated like that. And you're going to get the value of C. Okay? So we know the characteristics of our accelerometer. We need that because when you want to read the voltage reading out of that gadget, you have to multiply it by omega n squared, and that's why we need to know this. Okay. And the stiffness of that spring that is sitting there, you just plug it in based on the formula that we know between natural frequency and the stiffness in it. Now, guess what? 2,000 years ago, this fellow in China invented a device that, although still even now we cannot predict when the earthquake is going to come, but this detects uh, this detects uh, the occurrence of an earthquake. So he basically invented, I don't want to say accelerometer, but the first seismometer which uh, detects land motion. Now, this is a replica of that thing, about 2,000 years ago, from a long way. Let's do another example. Here is a typical thing that actually, this is the electronic one. This is the old-fashioned one, which actually shows you the land movement, the ground movement. Okay, up and down. Okay, it records it, and this basically these are relative motion. Okay, uh, remember these are the Z values that you're plotting here. Okay. So let's see, a seismometer having natural frequency of 4 rad per second. So we know that for our transducer, our gadget, seismometer, omega n is 4 rad per second. And we know its damping ratio. The damping ratio is, remember, we can estimate the damping ratio of something like that by doing logarithmic decrement and things like that. Now, it's mounted on a structure, this structure that is vibrating sinusoidally, harmonically up and down. If the difference between the maximum and minimum recorded value is 8, in other words, these amplitude, this differences is 8 millimeters. By the way, this is double the amplitude. Okay, peak to peak is 8, so the amplitude is half of that 4. Find the amplitude of displacement of the structure when its frequency is 40 rad per second. So when the ground is shaking at 40 rad per second, find out what the amplitude of displacement of the base is. Okay, good. So we are in the seismometer range. Okay, and basically this is the formula that we had. Measured displacement was 4 millimeter. True displacement is what you want to find. And you've got the stuff on the right hand side. First of all, let's find the frequency ratio because we need to plug it in here. It's omega b over omega n. You're told that the ground moves up and down at that frequency, and the machine has a natural frequency, seismometer has a natural frequency of 4, so R is 10. So you are actually in the seismometer range, remember, that's good. And uh, otherwise, what we wrote down is not true. Okay. So 4 over big Y that we are trying to find, we just plug in the values and get the big Y, which is 3.06. The ground or that gadget is moving up and down at as a unit, that platform as a unit, which is 3.06 millimeter. Okay. Now, later on, we will do an entire lecture on vibration isolation uh, or vibration absorber. So, uh, you know from your experience that if something is kind of moving a lot, if you want to damp out or kind of control that vibration, you put it on springs, and that will help. You already know that. Okay. However, this is called a passive vibration control. Now, there are active vibration controls that it requires an actuator. Of course, you need a sensor, and you need sensor to pick up the vibration, and when it has to activate the actuator. So when the building tries to, for example, to move to the right, just hypothetically, this actuator pushes it to the left. So it actively cancels the effect of. You must have heard about active noise cancellation. These headsets that they use that technology, is the same idea. So active vibration control absorbers require an actuator, but the passive ones is just just the mass, just the spring and damper, and therefore. So let's move on. There is some information. These are taken from Dr. Novak's classes. Uh, okay, so these are slides taken from Dr. Novak's course when he offers it, and it shows you some real world vibration levels. For example, on a calm day, basically the vibration, the G, the acceleration is of the order of 10 to the minus 6 G, 10 to the minus 6 G, very small number. We're talking about perhaps the vibrations that appear in a washing machine, 1G, and then there's an explosion here, which is 10 to the 6G. Now, there is another scale. There is another scale which is called decibel scale. So you look at the expression for decibel scale is 20 log of acceleration in G divided by some reference temperature. And that reference temperature really is this number that we're talking about. So, for example, if you look at this explosion taking place, uh, if this happens to be the G that is resulted from that, let's say, explosion, we have a million G here divided by 10 to the minus 6 G, and this is going to be 240. So the corresponding thing in decibel level is 240 decibel. Or if you look at, for example, this other case where the calm day, the G, the vibration level, being 10 to the minus 6, you plug it in here, you get a log of 1 basically, which is 0. So very frequency acceleration is specified in units of G, in other words, multiples of G, but it also can be done in terms of the dB. Particularly, this dB scale is particularly important in acoustic applications. Now, in general, this can be applied to any variable. For example, x can be displacement, not necessarily the acceleration. Here, the way it's described is as if it has to be an acceleration. Can be displacement or velocity, but you need a reference value. So in general, it comes from that expression. Now, when it comes to measuring, vibration level, essentially there's a few things involved here. Of course, there is a transducer, the accelerometer, which can be the classical one, which is defunct these days, or the piezoelectric one. And then there's a preamplifier, because what comes out of this is a voltage. And remember, I just want to point out that these days, if you install this and you attach it, I mean, through this chain to an output, you're going to see actually the acceleration level. You're not going to need to know the value of omega n, in other words, the natural frequency of your transducer, and then take something and multiply by it. This is all done internally, and therefore, although I said that you need to know the characteristics of your transducer in order to be able to, actually uh, get the accelerations that you're targeting. However, this is all done internally. In other words, your gadget, your transducer, does have a natural frequency and some of the characteristics that is all in the data sheet when you bought this gadget. Okay, you don't have to take omega and multiply it by something. But the range of applicability of this transducer will depend on that omega n and other characteristics. Now, this signal is very small, so you have to amplify it. And then when you amplify it, then there's take the noise out, and maybe you may have to do some averaging. These are all electronics, within the or digital signal processing and signal processing in general within the chain, in going from transducer all the way to output. And the output, you can see stuff in time domain or frequency domain and so this actually, the chain of measurement requirements in order to go from a physical phenomena to the prediction of it in terms of not prediction but detection of it through accelerometer. Now, uh, this drawing shows you the concept of piezoelectric, which is very robust. Okay, so when you take a piezoelectric crystal and you squeeze it like that in tension, or you shear it, okay, a voltage is generated, and this voltage eventually is going to turn into, of course, an acceleration that you want. Now, uh, there are other kinds of piezoelectric accelerometers, but this is the one that basically two planes shear. These red ones, the actual piezoelectric crystal is just let me see now, it's that piece, which is this blue thing in the middle, or it can be that it is annular shear. In other words, something that around it things will just shear this material, or it can be compression. So there's your piezo material. Uh, I'm thinking in this drawing, yeah, yes, you, this orange one is actually the mass, seismic mass. Remember, there is a mass in there which pushes on the crystal. And there's also this common delta shear configuration. There are other ones which I'm not record or displaying here. Now, the way the accelerometers are mounted, it can be through, for example, beeswax. You just put something very sticky between that and the gadget that you want to measure its acceleration, or it can be stud mounted. Okay, cementing the material, so using cementing material, cement the accelerometer to the thing that you want to measure. And of course, there's going to be differences in how, when it comes to certain regions, there may be differences, but still, any one of these can be used. Now, one thing for sure, you see, I'm not an experimentalist, but one thing that we all have to be aware of is that the accelerometers must be mounted on bearings. Do not put it on on directly on the shaft, uh, on the casing of the machine that you're trying to measure. So do not put it on mainly is to be mounted on bearings or the foundation. Okay, so that's why these are cropped out. This is on the shaft. This is on the casing. Uh, this one is good, which is mounted on the actually the bearing. The bearings right here. Okay, good. And there are things that affect the performance of the transducer. For example, the initial curved surface. There is humidity can affect things. There is acoustic noise, corrosive environment. If it's in the vicinity of magnetic field, strong magnetic field, that can affect the results here. And I don't want to go there, nuclear radiation. Now, I have a good example here to show you, and that is this is taken from this gentleman's lab video, and they noticed that a certain tractor, when it was at the idle stage, that idle stage, which basically nothing, engine is not running actively, would cause severe vibrations of the steering wheel. And they found out that actually uh, the uh, natural frequency of that steering wheel matched the natural frequency of the firing of the engines at the idle stage. So instead of basically changing the engine, they realized that you have to change the natural frequency of this steering wheel, and of course you just have to uh, do things to it so that the natural frequency of it does not match the frequency that is fit. It's coming from the idle state of the engine. And by doing that, of course, you dramatically reduce the vibration uh, of the uh, of the steering wheel. So the purpose of this lecture was to show you the basics of what you have learned in the design, how they pop up in the design of accelerometers. Of course, the illustration was made in reference to a very old-fashioned accelerometer, which is what I showed you initially. Let me see. Let me go back here, right there. As I said, these are generally speaking not used the way they are, because the piezoelectric ceramic is accelerometer is a lot more robust and durable, and has a much wider frequency range that it can be useful for than what I'm showing here. However, this allows us to write the equations which are needed in order to basically come up with the design of the accelerometer. Now, a couple of things you should know is that in the seismic region, the measured displacement, these are all in terms of voltages that are internally created from the piezo ceramic all the way to the display screen. Measured displacement over true displacement, the, the, the mechanics of it is that they're related to frequency ratio like that. This is why the R, natural frequency of the transducer, come into the picture, zeta, the damping, ratio of the transducer come into the picture, and of course the actual excitation of the base is in there because it's the numerator of R. So this is in the seismometer region. When you go to the accelerometer region, this translates into measured acceleration over true acceleration. So this is the fundamental equation that is used in solving problem for us. Okay, when it comes to saying something about the accelerometer that we have, and this is the accelerometer range, and this one is the seismometer range. Are you one really has to do these things on an everyday basis, and there are all kinds of things that you're going to run into. But this course is about showing you the fundamentals needed in vibration, and in this particular case, how those are applied in this particular lecture, how those are applied to the design of accelerometers or transducers. Okay, so that takes care of the lecture today, and please make sure you understand these some of these concepts. I mean, obviously, I don't expect you to be experts, but you should know the basics of what was done. This stuff will be on the test coming on Thursday. Thursday morning in the lecture, there is no new material. I will be doing several problems which I don't know may help you develop your confidence when it comes to writing a test a few hours later. Okay, good luck.